in the silent expanse of space, a visitor arrives from beyond the familiar boundaries of our solar system. Not a comet born of the sun's warmth, nor an asteroid forged in the crowded nursery of the inner planets. This interstellar object, 3I Atlas, cuts through the darkness with the quiet certainty of a messenger from distant stars. Its discovery, sudden yet precise, has awakened the attention of astronomers, planetary scientists, and dreamers alike, for encounters of this kind are extraordinary. The object moves with such speed and purpose that it defies ordinary expectations, carrying with it the weight of cosmic history and the enigma of origins unknown. As it arcs past Mars, a planet long studied and yet still mysterious, humanity waits in hushed anticipation, cameras poised, instruments calibrated, minds ready for revelation. The first images, though blurred and enigmatic, hint at the form of this cosmic traveler. A faint tale begins to whisper in the interplanetary void, an ephemeral signature of matter escaping into the vacuum, leaving a trail of curiosity in its wake. The trajectory is precise, almost unnervingly so, a line drawn with cosmic elegance across the plane of the planets. It is as if some unseen hand guided it, threading the needle of our planetary system with the skill of a master astronomer who never existed. And yet, there is no hand, only the immutable laws of physics shaping its path, laws that 3I Atlas seems simultaneously to obey and challenge. Size offers another layer of wonder. At an estimated 3 miles across, it dwarfs the bustling streets of Manhattan, yet in the grand theatre of the cosmos, it is but a speck, a fragment of ancient material travelling across light years, bearing secrets from other stars. Its composition, already a source of intrigue, presents anomalies that defy conventional understanding, a preponderance of nickel over iron, chemical signatures that do not align neatly with known cometry or asteroidal bodies. Scientists pause, noting the paradox. Could such a configuration arise naturally through processes unseen in our observational history, or does it hint at phenomena yet unimagined? Instruments stand ready. Mars orbiters and rovers, stationed across the rust-colored plains, turn their gaze toward this visitor. Each camera, each spectrometer, each minute of observation promises to yield glimpses of knowledge, pixels of understanding that, when combined, might reveal the nature of this interstellar traveler. The anticipation is palpable, a delicate tension between expectation and mystery, as humanity stands on the cusp of witnessing an event both ordinary in its cosmic mechanics and extraordinary in its implications. Above all, 3I Atlas invites reflection. Its journey reminds us of the vastness beyond our sun, the countless stars each nurturing their own debris, their own wanderers. It embodies the elegance and indifference of the universe, a solitary object tracing a silent path, oblivious to human observation, yet intimately entwined with our curiosity. As it passes Mars, so too does it pass through the imaginations of those who look skyward, inspiring wonder, speculation, and a profound awareness of our small but attentive place in the cosmos. In this moment, 3I Atlas is not merely an object, it is a narrative of distance, velocity, and the inexorable pull of discovery. The first glimmers of 3I Atlas were faint, ephemeral signals captured by the vigilant instruments that tirelessly scan the heavens. For weeks, the object remained a mystery, detected only as a subtle disturbance against the backdrop of stars, a fleeting smudge across the detectors of Earth's telescopes. Initial images were blurry, their details obscured by the immense distances and the limits of resolution, yet even these fragments whispered a story of something unusual, an interstellar traveler streaking silently into the inner reaches of our solar system. Scientists pored over every frame, each pixel a puzzle piece, trying to discern shape and structure, hoping for a hint of activity that might reveal its nature. Through this limited imagery, a tentative tail began to form, a ghostly appendage extending into the void. Unlike the familiar comas and tails of solar system comets, which are sculpted by the solar wind and the warmth of the sun, this nascent trail suggested a different dynamic. Material, small particles, gas, or perhaps something more exotic was being shed, yet the mechanism remained enigmatic. Observers noted the orientation and luminosity of the tail, searching for patterns, any clue that might anchor the object within our known frameworks. The tail was subtle, almost imperceptible at first glance, but persistent, hinting at processes at work that were simultaneously familiar and alien. Compounding the mystery were the preliminary spectroscopic readings. Instruments aboard orbiters and ground-based telescopes indicated chemical compositions that defied immediate categorization. A surprising abundance of nickel was noted, far exceeding the levels typically found in comets or asteroids of our solar system. Conversely, iron, which one might expect in comparable ratios, was conspicuously scarce. This unusual chemical signature raised questions. Was 3I Atlas a fragment of a larger, differentiated body from another star system? Had it undergone processes, collisions, heating, radiation exposure unseen in our own neighborhood? Every observation deepened the puzzle, urging scientists to consider explanations both natural and extraordinary. Even the very act of detection became an intricate dance between technology and patience. Observatories coordinated across continents, orbiters adjusted instruments, and teams waited for optimal viewing windows, mindful of the object's rapid motion. Unlike typical comets that drift slowly through the inner solar system, 3I Atlas was a visitor, moving with such velocity that every second of observation mattered. Each image required careful calibration, cosmic coordinates precisely mapped, background stars subtracted, and instrumental noise accounted for. What emerged from this painstaking process was a collection of glimpses, a mosaic of blurred light and spectral lines, enough to confirm presence, hint at structure, and yet leave the fundamental question unresolved. What exactly is this enigmatic traveler? As the world watched, even casual observers became witnesses to a rare celestial event. News outlets reported on the object, emphasizing its interstellar origin and the imminent flyby of Mars. But the scientific community understood that these preliminary images were the opening chapter, not the conclusion. The blurred shapes and tentative tail were symbols of both limitation and potential. They were reminders of the challenges inherent in studying the distant and unknown, and of the extraordinary discoveries that patience, precision, and relentless observation could eventually yield. In the quiet spaces between these pixels, the universe whispered secrets, and 3I Atlas, moving with inscrutable purpose, invited humanity to listen more closely than ever before. Size, in the cosmos, is a relative concept, but it is also a powerful lens through which we measure significance. For 3I Atlas, early estimates placed its width at roughly 3 miles, comparable, yet slightly larger than the span of Manhattan Island. To envision it on the streets of New York is almost surreal, a block of cosmic rock, a self-contained worldlet, traveling through the emptiness with silent momentum, invisible to the naked eye yet colossal in its implications. Against the vastness of the solar system, 3 miles might seem insignificant, a mere dot adrift among planets and moons, yet for instruments on Earth and Mars, every meter of that span is a canvas of material, history, and potential information. This scale, when combined with the object's velocity, approximately 60 kilometers per second, renders 3I Atlas both immense and ephemeral. Unlike local asteroids, whose gravitational interactions are well studied and whose orbital paths are predictable, This interstellar traveler pierces the solar system at a speed that outpaces our fastest human-made machines by hundreds of times. The combination of size and speed challenges our ability to observe it in detail. Every photograph captures only a fraction of its surface, every spectrum a fraction of its composition. Yet even these fragments, when interpreted with careful scientific analysis, allow astronomers to begin reconstructing a narrative of origin, motion, and potential composition. The size of 3I Atlas is also a lens into its energetic behavior. An object of this mass, even a few billion tons, carries enormous momentum. As it sheds material evidenced by the emerging tail, each particle represents the liberation of stored energy, the slow unspooling of a story written long before the solar system existed. Calculations suggest a mass of roughly 33 billion tons, a figure derived from observations of its minimal deceleration as it loses matter. The implication is that this is not a fragile wanderer easily perturbed by the sun's gravity or radiation pressure. It is a robust traveler, shaped over eons to withstand the vacuum and chill of interstellar space, and yet intimate enough that each particle it releases can be traced and analyzed by human instruments. The human tendency is to visualize such cosmic scales in familiar terms, and yet even the comparison to Manhattan is only a start. In the cosmic theater, where Mars looms like a dusty sentinel and Earth spins silently in its orbit, 3I Atlas is a messenger from beyond, its 3 miles of width a bridge across light years. Each kilometer of surface may hold geological heterogeneities, perhaps zones enriched with nickel, sparse in iron, hinting at processes far removed from our own solar history. Each rotation, each fragment of material lost, becomes a cipher, a clue to conditions in another planetary system, a record of collisional events, and a test of our understanding of physics applied across interstellar distances. Yet size is more than physical measurement. It is perception. For those monitoring 3I Atlas from orbiters around Mars, from ground-based telescopes, or from distant vantage points on Earth, the object's dimensions convey both awe and urgency. A 3-mile expanse, traveling at 60 kilometers per second, is more than a statistic. It is a spectacle of kinetic elegance and a reminder that the universe is a realm where scale and speed intertwine, where the very notion of big is contingent upon context, and where a solitary object can command the attention of a planet's observers with the silent weight of its passage. In this way, 3I Atlas, through its mere dimensions, bridges the human imagination and cosmic reality. It invites contemplation of distance, velocity, and mass, while simultaneously inspiring a recognition of our own observational limitations. Its size is both an invitation and a challenge, an invitation to ponder worlds beyond our own, and a challenge to discern, measure, and understand the subtle signatures it leaves in its wake. The very enormity and minuteness of its presence encapsulate the paradox of interstellar study, the profound significance of a small traveler hurtling through the dark, a 3-mile fragment of an unknowable expanse. Composition, in celestial terms, is a window into origin, history, and the processes that sculpt matter over billions of years. For 3I Atlas, the window is peculiar and compelling, revealing anomalies that have sent ripples of curiosity through the astronomical community. Unlike typical solar system comets, which present a mixture of ice, silicates, and trace metals, 3I Atlas exhibits an overabundance of nickel, while iron, a staple in rocky bodies, is strikingly deficient. This unexpected chemical signature challenges established assumptions, prompting scientists to reconsider how interstellar objects form, evolve, and survive in the cold depths of space. The prevalence of nickel over iron carries profound implications. Nickel is a metal that often forms in high-temperature environments, coalescing in the cores of planets or in the aftermath of supernovae, where immense pressures and temperatures enable nucleosynthesis. Its relative excess in 3I Atlas hints at processes either violent or rare, perhaps taking place around other stars, under conditions unfamiliar to our local planetary system. Iron, comparatively missing, raises questions. Was it stripped away by prior collisions? Has radiative or magnetic influence selectively removed it? Or does this object originate from a region of space where the chemical abundances differ fundamentally from our own solar neighborhood? Each scenario is tantalizing and speculative, yet grounded in real astrophysical principles. Observations also suggest the shedding of this nickel into space, forming the subtle tail seen from Earth-based telescopes and orbiters around Mars. This process, while analogous to cometary outgassing, deviates in composition and mechanics. Unlike water ice evaporating under solar heating, the loss of nickel-rich material implies a resistance to conventional sublimation and a potential fragility in the surface layers, perhaps due to microfractures, cosmic ray bombardment, or thermal stress accumulated over interstellar travel. The ejected particles, microscopic yet numerous, scatter light, giving astronomers a spectral fingerprint from which elemental abundances can be inferred. Further anomalies emerge in the spectral lines detected by advanced instruments. Minor emissions and absorptions hint at compounds that do not neatly correspond to the catalogued signatures of comets, asteroids, or meteoroids known to originate within our solar system. These spectral mysteries deepen the intrigue. Is 3I Atlas a purely natural object forged by exotic astrophysical conditions, or might it carry evidence of processes, geological or technological, that we have yet to comprehend? Such questions are not merely academic. They provoke rigorous observational campaigns, prompting astronomers to recalibrate instruments, verify data against potential contamination, and scrutinize every photon that reaches their detectors. This anomalous composition also interacts with the object's motion. Nickel, being denser than ice or silicates, affects momentum differently, influencing the acceleration or deceleration of ejected material. Understanding these dynamics becomes crucial not only for modeling its trajectory past Mars, but also for extrapolating its internal structure, cohesion, and potential for fragmenting under gravitational or thermal stress. Each observation feeds a complex feedback loop. Composition informs dynamics, which informs origin, which informs future expectations for observation and theoretical modeling. Ultimately, 3I Atlas's chemical signature is more than a curiosity. It is a narrative thread linking its present journey to a broader cosmic history. Every atom of nickel, every absence of iron, whispers secrets of formation, survival, and the diverse conditions of interstellar space. For astronomers, each spectral anomaly is a clue in an unfolding mystery, inviting reflection on the unexpected richness of the universe and the limitations of our current understanding. In this subtle interplay of elements, light, and motion, the object stands as both messenger and puzzle, its composition a siren call to human inquiry, drawing attention to the wonders and enigmas that lie beyond our planetary cradle. The trajectory of 3I Atlas presents a profound puzzle, one that challenges assumptions about interstellar wanderers and their interactions with planetary systems. Unlike the random, hyperbolic paths often associated with comets entering the solar system from distant reaches, this object's orbit is remarkably aligned with the plane of the planets. It traces a path that sweeps close to Mars with uncanny precision, a line almost geometrically drawn, slicing through the ecliptic as if guided by some invisible principle. This alignment is not only statistically rare, it defies easy explanation and has prompted scientists to reconsider the dynamics of interstellar object passage through established gravitational frameworks. Ordinarily, interstellar objects arrive from arbitrary directions, their velocities shaped by the gravitational influences of their origin stars, galactic tides, and encounters with other masses. The vast majority do not approach the inner solar system along a trajectory that lies close to the planetary plane, and yet 3I Atlas does. This alignment amplifies the sense of mystery, forcing astronomers to ask questions that extend beyond simple celestial mechanics. Is the trajectory a coincidence, the result of chance encounters over millions of years, or is it indicative of a selective process, a natural funneling effect that directs certain objects into planetary planes across galaxies? Each possibility carries implications for our understanding of both local and interstellar dynamics. The path itself is further complicated by the object's extreme velocity. Traveling at 60 kilometers per second, it races past Mars in a matter of hours, its momentum largely impervious to the subtle gravitational nudges of the Sun or planets. While the object's motion can be modeled as hyperbolic, the degree of its precision in intersecting the ecliptic adds layers of uncertainty. Small observational errors in initial velocity or position could result in significant divergence over the millions of kilometers it has traveled. Yet, repeated calculations confirm that it is on course, a testament both to the object's persistence and to the meticulous accuracy of contemporary orbital tracking. Observers around the world, from ground-based telescopes to Mars orbiters, focus on the delicate timing of this flyby. The alignment allows for optimal imaging windows, where high-resolution instruments may capture the object against the Martian backdrop. These observations are not merely aesthetic. The trajectory directly informs models of mass, shape, and surface composition. By analyzing slight deviations in motion as 3I Atlas interacts with the gravitational fields it encounters, scientists can infer density distributions, potential outgassing events, and even internal structural integrity. Every curve, every acceleration or deceleration becomes a clue in reconstructing a story billions of years in the making. Moreover, the trajectory opens broader philosophical considerations. The object's passage along a plane so familiar to Earth's own orbit, so aligned with the very plane in which we reside, evokes questions about the interconnectedness of planetary systems across the galaxy. Is this a cosmic accident, or do such alignments occur more frequently than we have yet observed? For humanity, watching a 3-mile interstellar traveler glide along a path so precisely coordinated with our planetary plane is an invitation to contemplate chance, order, and the hidden harmonies that govern motion on the grandest of scales. 3I Atlas, through its trajectory, reminds us that even in the seeming chaos of the cosmos, there exists the possibility of patterns that both astonish and challenge our understanding. Velocity is a language the universe speaks fluently, and 3I Atlas converses with it in a dialect few human instruments can fully comprehend. Traveling at 60 kilometers per second, approximately 600 times faster than the fastest race car on Earth, it is a messenger from a distant star system, carrying with it both the inertia of interstellar space and the record of its violent, enigmatic history. At this speed, distances that would seem insurmountable in human terms, millions of kilometers are crossed in hours. Every second of observation becomes critical, every measurement a delicate negotiation with time and motion. The extreme velocity intensifies the observational challenges. Conventional imaging techniques rely on extended exposure to capture faint light, but for an object moving this rapidly, exposure times must be carefully adjusted to avoid motion blur that could obscure critical surface details. Spectrometers and photometers are similarly constrained, requiring precise timing and calibration to ensure that the rapid passage does not compromise the integrity of chemical and structural data. The dance between speed and observation is intricate, a careful choreography orchestrated across continents and orbiters, where human patience is measured in milliseconds and cosmic movement in kilometers per second. High speed also magnifies the dynamic consequences of mass loss. The faint tail observed trailing 3I Atlas is not merely a visual signature, it is a record of interaction between the object and the solar radiation it encounters. At 60 kilometers per second, even small particles ejected from the surface are swiftly accelerated, forming trails that may curve, disperse, or reflect light in unexpected ways. By studying these particles, scientists hope to reconstruct not just composition, but also the mechanics of release, inferring the strength and cohesion of the outer layers, and perhaps revealing microstructural anomalies that challenge conventional models of interstellar material. This velocity further informs philosophical reflection on scale and perspective. In a single hour, 3I Atlas travels a distance greater than the entire width of Earth's orbit around the Sun in some fractions of days, a reminder of the vastness and dynamism inherent in the cosmos. For observers on Mars and Earth, this fleeting presence so rapid, so transient, becomes a meditation on the impermanence of encounters in space. Objects that have journeyed for millennia across interstellar distances can appear, interact briefly with our instruments, and vanish, leaving behind data, speculation, and awe. Beyond mechanics, the speed introduces the potential for extraordinary phenomena. Collisions with stray interstellar dust, thermal shock from solar heating, or magnetic interactions with the Sun's field can have amplified effects at these velocities. Each influence, minute on its own, is magnified by motion, shaping the tail, altering the spin, or subtly affecting the trajectory. These forces, interacting with the object's anomalous composition, create a web of complexity that challenges both observation and theory. Astronomers must disentangle the interplay of speed, mass, composition, and external influence to derive meaningful models of behavior. Finally, the velocity serves as a narrative device in our understanding of 3I Atlas. It emphasizes its otherworldly origin, the remoteness of its birthplace, and the sheer improbability of encountering it in the relatively narrow window when Mars lies along its path. The object is not merely fast, it is swift across time, bridging light years in a blink relative to human lifespans. In its passage, it embodies both the grandeur of cosmic motion and the urgency of discovery, urging observers to act with precision, to anticipate its fleeting presence, and to glean from its speed the stories encoded in its composition, trajectory, and ephemeral tail. The first human eyes, or rather instruments tasked with observing 3I Atlas, were both numerous and sophisticated, spanning the globe and extending to robotic sentinels orbiting Mars itself. Ground-based telescopes, long attuned to the rhythms of familiar planets and comets, turned toward the interstellar visitor, seeking photons that had traveled across light years to reach our detectors. Each facility offered a distinct perspective. Some captured broad motion across the starfield, others refined the faint spectra that hint at elemental composition. Collectively, they formed a web of observation, an intricate network poised to unravel the mysteries of a traveler not bound to the Sunday. Above the red plains of Mars, orbiters joined the vigil. NASA's Mars Reconnaissance Orbiter, with its high-resolution imaging science experiment, readied its instruments, calibrated to capture details as small as 30 meters per pixel, a remarkable feat considering the object's fleeting approach. European Space Agency assets, such as Mars Express, complemented these observations, each contributing spectral analyses, imaging data, and telemetry. Even rovers, designed for geological surveys, prepared to intercept reflected sunlight from the interstellar object, their cameras recording the ephemeral interplay of light and motion as 3I Atlas swept past. In this coordinated ballet, human ingenuity extended across planetary boundaries, enabling a multidimensional examination of an object that existed far beyond our immediate experience. The orchestration of these observatories required precise timing and prediction. Every orbital calculation, every trajectory model was scrutinized to anticipate where and when 3I Atlas would appear in each instrument's field of view. The object's extreme velocity, coupled with its unusual path aligned to the planetary plane, demanded synchronization at a level reminiscent of a global symphony. Teams of astronomers worked in shifts around the clock, sharing data in near real time, correcting for atmospheric distortion, instrument drift, and the faint background light of distant stars. Each photon captured was precious, a fragment of the story that could illuminate the object's nature, origin, and behavior. These observatories also served as human proxies, extending our senses into regions inaccessible to the naked eye. They transformed fleeting light into meaningful data, spectroscopic lines hinting at elemental ratios, subtle elongations suggesting mass loss, minute brightness variations that might indicate rotation or surface heterogeneity. Each measurement was a bridge between the incomprehensible scale of interstellar travel and the practical constraints of human observation, a testament to our capacity to reach across vast distances through the careful application of technology and physics. Moreover, the presence of these instruments introduced a philosophical layer to the encounter. While 3I Atlas drifts oblivious to Mars or Earth, humanity engages in an intimate act of attention, tracing its passage, dissecting its composition, and seeking meaning in its trajectory. The object is both distant and close, alien and familiar, its very observation a reflection of curiosity and persistence. In the interplay of orbiters, rovers, and telescopes, one perceives a form of quiet dialogue. Light from billions of kilometers away carries information. Human ingenuity interprets it. The universe, in turn, reveals its subtle secrets in a measured cadence, tempered by distance, velocity, and precision. Through this network, 3I Atlas is not merely a passive wanderer, it becomes a participant in a human quest for knowledge. Every pixel, every spectrum, every adjustment of a telescope mirror represents an act of engagement, a willingness to meet the unknown on its own terms. The instruments become extensions of both our eyes and our imagination, translating the object's silent journey into data, hypotheses, and narrative. And as the interstellar traveler approaches its closest pass by Mars, this ensemble of observers stands ready, poised to capture fleeting insights, to translate motion into meaning, and to ensure that this brief encounter is recorded in the annals of astronomical discovery. With observations underway, scientists turn to quantifying 3I Atlas's mass and physical characteristics, a process that combined meticulous measurement with sophisticated modeling. Early calculations estimated its mass at roughly 33 billion tons, a staggering figure for an object only 3 miles across. Such density implied a compact, robust structure capable of withstanding both the frigid vacuum of interstellar space and the dynamic forces encountered within the inner solar system. Determining mass required not direct measurement, of course, but careful inference, tracking the object's motion as it shed particles, observing the subtle deceleration, and modeling the influence of solar gravity and radiation pressure on its trajectory. These estimates of mass, when paired with the object's speed, revealed a remarkable momentum, one that constrained hypotheses about its composition and structural integrity. The abundance of nickel, contrasted with the relative paucity of iron, suggested a differentiated origin, perhaps the remnant of a larger body that had undergone significant thermal or collisional evolution. Each theoretical model had to account not only for the observed elemental ratios, but also for the resilience of the object as it approached the inner planets, where radiation and gravitational gradients would otherwise induce fragmentation. The convergence of composition, size, and speed painted a portrait of 3I Atlas as an interstellar survivor, a relic of processes unfolding in distant stellar systems now temporarily intersecting our planetary neighborhood. Modeling the object's physical characteristics also required simulating the effects of mass loss. Observers had detected the early formation of a tail, indicative of material escaping from the surface, likely under solar heating and particle interactions. By estimating the mass of ejected nickel and the rates at which it was lost, scientists refined their understanding of the object's internal cohesion and surface structure. Even small variations in density could dramatically alter predictions of rotational stability, trajectory deviations, and particle ejection patterns. In essence, every fragment of material became a data point in reconstructing a three-dimensional understanding of a body moving hundreds of millions of kilometers from its point of origin. These calculations were not abstract exercises. The trajectory past Mars, the opportunity to image the object with high-resolution instruments, and the potential for spectroscopic analysis all depended on precise mass modeling. By integrating orbital mechanics, rotational dynamics, and compositional analysis, astronomers produced a set of predictive models to guide observational strategies. Every adjustment in exposure time, every alignment of a spectrometer, relied on these foundational calculations. The object's mass, in conjunction with its anomalous chemical composition, became a critical parameter shaping the scientific campaign and dictating which instruments could yield meaningful results. The process also underscored the interplay between data and theory. Observational uncertainty necessitated multiple models, each incorporating assumptions about density, surface composition, and material strength. As data streamed in from orbiters and Earth-based telescopes, models were iteratively refined, confirming some predictions while challenging others. This iterative cycle exemplified the scientific method at its most dynamic. Hypotheses grounded in physics, continually confronted by observation, adjusted in light of evidence, and forever incomplete until direct, high-resolution imagery could fill the remaining gaps. Through this lens, 3I Atlas became both subject and teacher, instructing humanity in the intricacies of interstellar physics and the delicate art of inference at cosmic scales. Finally, these calculations fostered a deep appreciation for the subtlety of the universe. An object, 3 miles across, can carry billions of tons of matter, travel at incomprehensible speeds, and yet slip past our instruments almost unnoticed. The endeavor to measure, model, and understand it reflects not only technological capability, but also philosophical engagement, a recognition that even the smallest points of light, traveling silently through space, can illuminate profound truths about matter, motion, and the diversity of worlds beyond our Sunday. Beyond calculations and observations lies the profound question that haunts astronomers and theorists alike. Is 3I Atlas purely a natural object, or could it conceal traces of artificial origin? While the preponderance of evidence points to a body forged through natural astrophysical processes, the anomalies in its composition, trajectory, and potential energetic outputs invite speculation. The overabundance of nickel relative to iron, the precise alignment with the planetary plane, and the possibility of correlations with the historic WOW signal collectively nudge the imagination toward possibilities that challenge conventional categorizations. Natural explanations remain the leading hypotheses, and they are compelling. Astronomers consider 3I Atlas as an interstellar fragment, perhaps ejected from the outer regions of another star system, shaped over eons by collisions, radiation, and thermal cycling. In this view, its unusual composition could result from selective processes within its parent system, differentiation in a protoplanetary body, partial melting, or the stripping of volatile layers during ejection. The trajectory, though statistically improbable, could be the outcome of gravitational perturbations during its interstellar journey, a cosmic roll of the dice that fortuitously aligns with Mars's orbit for this brief encounter. Yet the anomalies continue to provoke debate. The object's velocity, unusually high even for interstellar visitors, combined with its chemical peculiarities, has prompted some to consider alternative explanations. Could it harbor a compact internal energy source, a relic of technological construction, or a naturally occurring nuclear-like reactor embedded within its mass? While speculative, the concept is grounded in physics. A sufficiently dense metallic core could, under the right conditions, generate detectable energy emissions, including low-level radio signals. The possibility, however remote, compels careful measurement and monitoring, as the implications extend beyond mere curiosity into the domain of profound philosophical and existential reflection. This tension between natural and technological interpretations is compounded by historical coincidences. The alignment, within 9 degrees, between 3I Atlas and the direction of the 1977 WOW signal introduces a probability so low, approximately 0.6%, that it cannot be dismissed lightly, yet it remains within the bounds of statistical chance. Scientists must navigate between the extraordinary and the plausible, resisting the lure of sensationalism while acknowledging that nature itself often produces phenomena more bizarre than fiction. The dialogue between what is expected and what is observed becomes a mirror for human curiosity, illustrating both our desire to categorize and the universe's capacity to surprise. In practical terms, this debate shapes observation strategy. Instruments are calibrated not only to capture imagery, but also to detect any anomalous emissions, subtle magnetic fields, or patterns of material loss that might hint at processes beyond conventional physics. Each measurement, even when yielding null results, informs the probabilities and models, refining our understanding of what constitutes a natural object versus a potential artifact. In this way, 3I Atlas becomes a nexus for scientific rigor and imaginative exploration, challenging researchers to remain disciplined yet open-minded. Ultimately, the question of origin, natural or otherwise, is inseparable from the object's identity. It is not merely a mass of rock or metal, it is a symbol of the unknown, an emissary that forces humanity to confront the limits of our knowledge. By considering all possibilities, from the mundane to the extraordinary, scientists and observers alike engage in a dialogue that spans disciplines, from astrophysics to philosophy. In the enigmatic presence of 3I Atlas, the cosmos presents a puzzle that refuses simple resolution, demanding a balance between skepticism, curiosity, and wonder. To understand the significance of 3I Atlas, it is essential to situate it within the broader, historical context of interstellar visitors. Only 2 such objects had been confirmed in our solar system prior: Oumuamua in 2017, a slender, cigar-shaped traveler, and Comet 2I Borisov in 2019, with a more conventional cometary structure. Each arrival challenged astronomers, expanding the horizon of what interstellar debris could look like. Yet 3I Atlas brings a complexity that surpasses its predecessors in both scale and anomaly. While Oumuamua evoked curiosity through its elongated form and lack of outgassing, and Borisov through its familiar icy composition from a distant star, 3I Atlas combines size, composition, and trajectory in ways that defy neat categorization. Historical comparison also highlights the technological progression of observation. When Oumuamua appeared, detection relied on the Pan-STARRS survey, capable of discovering fast-moving faint objects, but images were limited and detail sparse. By contrast, 3I Atlas benefits from a constellation of observatories, both terrestrial and Martian, equipped with high-resolution cameras, spectrometers, and real-time telemetry. The technological leap allows for unprecedented data capture, the ability to measure subtle variations in composition, to track minute rotational shifts, and to observe material loss with precision. These advances mean that humanity is not merely witnessing a fleeting celestial visitor, but is actively reconstructing its physical and chemical narrative. The historical lens also emphasizes the rarity of interstellar encounters. Despite the vastness of space, the probability of an object entering the inner solar system along a trajectory conducive to detailed observation is exceedingly low. Past interstellar objects either passed quickly, at angles difficult for Earth-based instruments, or were simply too small to yield significant spectral information. 3I Atlas, by contrast, offers a convergence of favorable conditions, a relatively large size, a trajectory aligned with the planetary plane, and the presence of a network of modern observational tools. In this sense, it represents both a scientific opportunity and a moment of cosmic serendipity. Yet the historical record is more than chronology. It is a narrative of understanding, of learning to interpret what interstellar visitors can teach us about planetary system formation, galactic dynamics, and the diversity of materials in the universe. Each prior object offered fragments of insight, and 3I Atlas builds upon them, inviting questions about variability in composition, the prevalence of nickel-rich bodies, and the potential for anomalies that challenge existing models. By situating it in this lineage, scientists can assess patterns, test hypotheses about formation mechanisms, and refine simulations of interstellar ejection processes. Moreover, historical context provides perspective on human response. Each interstellar object has catalyzed collaboration, dialogue, and debate across institutions and continents, revealing both the strengths and limitations of our observational and analytical capabilities. 3I Atlas, as the latest in this sequence, continues the tradition, amplifying the intersection of data, theory, and speculation. It prompts reflection on how far astronomy has progressed in mere decades, how instrumentation has evolved to capture fleeting, distant phenomena, and how each new visitor expands the frontier of knowledge while preserving the essential enigma of the cosmos. Through this historical lens, 3I Atlas emerges not as an isolated anomaly, but as part of a continuum of discovery, a chapter in the ongoing story of human engagement with interstellar matter. Its passage past Mars is not merely an event in space and time, but a milestone in the collective effort to comprehend objects that originate far beyond our solar neighborhood. By understanding its place in this lineage, observers and theorists alike gain perspective on both the object itself and the broader tapestry of interstellar exploration, appreciating the delicate balance of chance, preparation, and cosmic motion that brings such mysteries into view. With the historical framework established, attention turns to the strategies devised for observing 3I Atlas. The orchestration of observation campaigns is as much an art as a science. requiring the alignment of instruments, personnel, and timing with the object's rapid, transient passage. Each telescope, whether ground-based or orbital, was tasked with a precise role, capturing complementary data that would later converge into a coherent understanding of the interstellar visitor. Exposure times, spectral filters, and pointing coordinates were calculated with painstaking care, as even a minor misalignment could result in blurred images or missed signals. High-resolution cameras on Mars orbiters were particularly critical. Instruments like NASA's High-Resolution Imaging Science Experiment, HiRISE, were capable of resolving features down to tens of meters, sufficient to discern variations across 3I Atlas's surface that would be impossible from Earth alone. These instruments aimed not merely to track the object, but to capture subtle brightness variations that could reveal rotation rates, shape irregularities, or localized material shedding. Every image was expected to yield multiple layers of insight: surface texture, albedo contrasts, and hints of compositional heterogeneity. Planning such observations demanded simulation of the object's apparent motion across the instrument's field of view, accounting for both its velocity and the motion of the orbiter itself. Simultaneously, spectrometers measured the wavelengths of light emitted or absorbed by the object, teasing out elemental and molecular composition. Each spectral line, often faint and buried within background noise, required careful calibration and cross-referencing against known atomic signatures. Observers sought confirmation of the anomalous nickel abundance, detection of any rare compounds, and the potential presence of transient phenomena, such as bursts of gas or dust that might indicate localized surface activity. These measurements would later feed into models of 3I Atlas's formation and evolution, informing hypotheses about its origin in a distant star system. Ground-based observatories complemented orbital observations, providing broader temporal coverage and cross-validation. Surveys employing wide-field cameras captured the object's motion against star fields, while photometric instruments monitored brightness fluctuations. Coordination between facilities allowed for continuous tracking despite the object's rapid movement and the limitations imposed by diurnal cycles, weather, and instrument availability. Observers communicated in near real time, adjusting exposure times and pointing strategies as preliminary data refined predictions of trajectory and orientation. The observation strategy also incorporated contingency for unexpected anomalies. The rapid passage of 3I Atlas meant that any sudden outgassing, fragmentation, or anomalous reflection could only be captured if instruments were prepositioned and ready. Teams maintained alert protocols, prepared to adjust observational plans within minutes to capture ephemeral events. In this way, the campaign became not just a technical endeavor, but a dynamic, responsive exercise in cosmic anticipation, blending precision with adaptability. Finally, the strategy reflected a philosophical dimension. Observing 3I Atlas was more than a technical challenge. It was an exercise in patience, attentiveness, and humility before the cosmos. Each image and spectrum represented a momentary bridge between human perception and the vast interstellar distances from which the object originated. The coordinated effort of instruments, humans, and computational models embodied the delicate interplay between observation and interpretation, where meticulous planning converges with the unpredictable nature of the universe to reveal insights into a traveler that had journeyed across light years to intersect our gaze. As data streamed in from orbiters, telescopes, and rovers, a new layer of mystery emerged, signals that seemed to hint at something beyond mere cosmic debris. Observers noted subtle emissions, faint radio bursts that, while within the bounds of natural phenomena, raised compelling questions. the discussion inevitably turned to the 1977 WOW signal, a historic moment in astronomy when a brief, intense radio signal appeared, unmatched by background noise and never repeated. While initially considered an anomaly, the similarity in directional alignment with 3I Atlas was remarkable, prompting renewed attention to possible correlations between the interstellar object and the enigmatic signal. The WOW signal had arrived from deep space, a complex sequence of characters encoded in intensity rather than content, a transient whisper from an unknown source. Its strength, 30 times that of background noise, had captivated astronomers and fueled speculation about extraterrestrial intelligence. For decades, it remained unresolved, a puzzle stored in the annals of observational astronomy. The emergence of 3I Atlas in a similar sector of space offered, for the first time, an object whose position and motion could be precisely modeled against the original signal's source. The potential alignment, calculated to within 9 degrees, suggested a coincidence improbable enough to demand rigorous examination, yet not conclusive enough to assert causation. Scientific inquiry into this alignment required meticulous analysis. Researchers reconstructed the past trajectory of 3I Atlas, tracing its path backward in time to estimate its position in 1977. Remarkably, the object was located approximately 3 light days away from Earth at that time, a distance that implied that any signal emanating from it would have required significant power to reach our detectors. Estimations suggested energy outputs comparable to a gigawatt, akin to the output of a terrestrial nuclear reactor. While speculative, this calculation grounded the discussion in physics, quantifying what would be necessary for such a coincidence to produce an observable effect. Simultaneously, the compositional anomalies of 3I Atlas, its nickel-rich structure and relative paucity of iron, added nuance to the debate. Could these characteristics support a mechanism for generating detectable signals, whether naturally through energetic processes or hypothetically through technological means? Researchers considered both possibilities with caution, mindful of the scientific imperative to avoid premature conclusions. The juxtaposition of historical signal data with contemporary observations created a rare opportunity, a bridge between decades of curiosity and the immediate precision of modern instruments, allowing hypotheses to be tested against both temporal and spatial constraints. The discussion extended beyond technical analysis into philosophical reflection. The alignment with the WOW signal, whether coincidence or causation, exemplified the universe's capacity to surprise, to interweave events across decades and distances in ways that challenge human expectation. For astronomers, it was a reminder of the provisional nature of knowledge. What was once recorded as an anomaly might, in the light of new discovery, gain context and meaning. It also underscored the tension inherent in interstellar study, where the line between natural explanation and extraordinary speculation is both necessary and delicate. Ultimately, these unexpected signals reframed the encounter with 3I Atlas. The object was no longer merely a physical presence passing near Mars. It became a point of historical and scientific resonance, connecting past mysteries with present observation. Every measurement, every spectral line, and every trace of motion gained additional weight, informed not only by immediate data, but by decades of human curiosity about the cosmos. In this interplay between object, signal, and observer, the boundaries of possibility expanded, reminding humanity that the universe holds surprises capable of bridging time, space, and imagination in ways both subtle and profound. The alignment between 3I Atlas and the historic WOW signal demands careful scrutiny, not merely for its improbable coincidence, but for the implications it carries for our understanding of interstellar phenomena. Statistically, The probability that a randomly incoming interstellar object would align so closely with a previously recorded signal is minuscule, approximately 0.6%, forcing astronomers to balance skepticism with wonder. This numerical improbability does not confirm causation, yet it does elevate the object's observational importance, suggesting that subtle correlations across decades and light years may reveal patterns previously unrecognized. Analyses of the object's trajectory reinforce this sense of alignment. Researchers meticulously reconstructed its position in 1977, accounting for gravitational perturbations, interstellar velocities, and solar system dynamics. The calculations revealed that 3I Atlas was not merely in the same general direction, but within a spatial corridor consistent with the WOW signal's origin. This coincidence prompted discussions about energy requirements. For a signal to have reached Earth from that distance, the source, whether natural or technological, would need to generate on the order of a gigawatt of power, comparable to the output of a terrestrial nuclear reactor. While entirely speculative, the exercise illustrated the magnitude of energy involved and grounded the discourse in physical realism. The directional alignment also has implications for observation strategy. Instruments tracking 3I Atlas could, in principle, monitor for faint radio emissions in the frequency bands of the original WOW signal, though no definitive detection had yet occurred. Even a null result would provide constraints on possible mechanisms, refining models of natural outgassing, energetic interactions, and particle emission that could mimic or generate radio signals. Scientists approached the endeavor with caution, designing experiments to maximize data while minimizing interpretive bias, aware of the seductive allure of sensational conclusions. In addition to technical considerations, the alignment evokes philosophical reflection. A solitary interstellar object, traversing the void for potentially millions of years, intersecting the path of a rare historical signal, serves as a reminder of the interconnectedness of space and time. It challenges the assumption that cosmic events are isolated, instead suggesting a subtle web of relationships, coincidences, and energetic interactions. For those observing from Earth or Mars orbit, the convergence of trajectory and historical signal is not merely a puzzle, but a meditation on contingency, pattern recognition, and the persistent human desire to find meaning in the universe's vast expanse. Furthermore, the alignment accentuates the tension between probability and possibility. The object's unusual composition, its rapid velocity, and now its potential connection to a decades-old signal amplify the enigma, compelling scientists to explore scenarios at the margins of conventional expectation. Could an object naturally produce conditions capable of generating detectable emissions? Might some rare astrophysical process, as yet unknown, be at play? While extraordinary claims require extraordinary evidence, the alignment serves as a catalyst for inquiry, a reminder that observation must remain open to both expected and unexpected outcomes. Ultimately, the directional alignment transforms 3I Atlas from a solitary visitor into a node within a network of cosmic events, a bridge linking historical curiosity and contemporary science. Whether the correlation proves meaningful or coincidental, it underscores the importance of precision, patience, and reflective interpretation in astronomy. Each data point, each measurement of position, velocity, or emission becomes part of a narrative that spans decades, connecting human observation to the vast and indifferent cosmos through subtle alignments, improbable trajectories, and the persistent quest for understanding. The consideration of power and energy required to produce observable phenomena introduces a striking dimension to the study of 3I Atlas. Calculations based on its distance during the 1977 WOW signal event indicate that if the object were the source, it would need to generate approximately a gigawatt of energy comparable to a terrestrial nuclear reactor. This magnitude, while extraordinary in human terms, is plausible within astrophysical contexts, where compact, metallic-rich bodies could harbor residual heat, radioactive decay, or other energy-converting processes. By grounding speculation in measurable physics, scientists maintain rigor even while exploring possibilities that border on the extraordinary. The notion of a naturally occurring energy source within 3I Atlas aligns with some astrophysical theories. Metallic cores, particularly those rich in nickel, could support localized heat generation through radioactive decay, producing energetic particles or thermal outflows. Over billions of years, such processes might create minor electromagnetic emissions, faint but detectable across interstellar distances if focused or transient. Alternatively, interactions with cosmic rays, stellar winds, or magnetic fields could generate sporadic bursts of radiation, adding nuance to the assessment of anomalous signals. Each hypothesis is carefully modeled against observational constraints, ensuring that conjecture remains anchored to plausible mechanisms. Simultaneously, the idea that energy could be harnessed or structured in a technological manner cannot be wholly dismissed, even if deemed improbable. The possibility, however remote, that an artificial device or probe might carry an onboard energy source capable of producing detectable emissions exemplifies the scientific principle of exploring all hypotheses, particularly when confronted with anomalies. It is crucial, however, to approach such speculation with stringent standards. No assumption of intent or intelligence is made, only the recognition that energy transfer mechanisms can be constrained and tested against observed data. This energetic perspective informs both observation and interpretation. Instruments tuned to radio frequencies, high-energy particles, and thermal emissions are deployed to capture any anomalies consistent with theoretical outputs. Even the absence of signals serves as valuable data, constraining models of composition, energy distribution, and potential internal processes. Each measurement, positive or null, reduces uncertainty, incrementally refining the understanding of the object's nature. In this way, energy considerations bridge the gap between raw observation and the theoretical modeling necessary to interpret 3I Atlas's behavior and potential origin. Philosophically, contemplating the energy scales associated with 3I Atlas underscores the vast contrast between human perception and cosmic reality. A gigawatt, immense by terrestrial standards, is but a fleeting pulse in the interstellar void, easily dwarfed by natural stellar and galactic processes. Yet for humanity, these calculations render the object tangible, allowing comprehension of its potential to influence measurements, produce detectable signals, or interact subtly with its environment. The mind grasps the enormity, even as the universe remains indifferent to observation, highlighting both our limitations and our ingenuity in bridging understanding through science. Finally, the exploration of power within 3I Atlas exemplifies the interplay of measurement, theory, and imagination. By quantifying energy requirements, scientists delineate the boundaries of plausibility, guiding both observation and interpretation. This careful integration of physics with inquiry allows humanity to confront anomalies responsibly, to remain open to extraordinary possibilities without abandoning empirical rigor. In considering energy, 3I Atlas transforms from a passive interstellar traveler into an active subject of scrutiny, its silent journey illuminated by calculations that span decades, light years, and the human desire to understand the universe's subtle messages. Mass and mechanics converge in 3I Atlas, shaping both its journey and the scientific narrative surrounding it. Observations of material loss, particularly the shedding of nickel, provide critical insight into the internal and surface structure of the object. Each particle lost, however minuscule, represents not merely mass but momentum, subtly altering the object's motion as it traverses the solar system. The rate and composition of ejection, combined with the object's high velocity, offer clues to its cohesion, density, and potential internal heterogeneity. Material loss is evident in the faint tail observed trailing 3I Atlas. Unlike typical cometary outgassing dominated by volatiles such as water or carbon compounds, the ejected particles are rich in metallic elements, implying a mechanical rather than purely thermal process. Fragmentation due to stress, surface microfractures induced by cosmic radiation, or thermal expansion from solar heating could liberate these particles, which then disperse into the void, forming an ephemeral signature that can be detected across astronomical distances. The dynamics of this shedding are complex. Small variations in particle size and velocity produce differing dispersal patterns, allowing observers to reconstruct aspects of the object's surface and internal structure. The mechanical stability of 3I Atlas is further informed by rotational dynamics. Its spin, inferred from variations in brightness, interacts with mass distribution to influence both trajectory and ejection patterns. Uneven mass or surface irregularities can induce precession or tumbling, affecting how material is lost and how momentum is redistributed. These mechanical considerations are not merely academic, they directly inform predictions of the object's path past Mars and potential interactions with the solar wind, planetary gravity, or interstellar particles. Understanding these dynamics is essential for both modeling and observation planning. Moreover, the interplay of mass, composition, and motion has implications for energy distribution. As nickel-rich fragments detach, kinetic energy is redistributed, generating subtle but measurable effects on rotation and trajectory. This process, combined with high-speed passage, results in a delicate balance. The object maintains structural integrity while continuously evolving through interaction with its environment. Observers use these mechanical signatures to infer density, internal cohesion, and potential anisotropies within the object, constructing a multidimensional portrait from subtle cues. Philosophically, the mechanics of mass loss invite reflection on impermanence and transformation. 3I Atlas, though massive and swift, is not static. It evolves as it journeys through space, shedding fragments, interacting with radiation, and subtly reshaping its trajectory. This dynamic interplay mirrors larger cosmic processes, where even seemingly stable bodies are subject to change. For scientists, the mechanics of the object provide both challenge and insight, requiring careful measurement and modeling to reconcile observation with theory. Finally, the study of mass and mechanics underscores the intimacy of observation. Every particle lost, every rotational shift, and every slight deviation in trajectory conveys information about an object millions of kilometers away. 3I Atlas becomes a laboratory in motion where physics, chemistry, and dynamics intersect, revealing not only the nature of a solitary interstellar traveler, but also the broader principles governing matter across the galaxy. Through meticulous study of its mechanics, humanity gains a tangible connection to an object that otherwise exists only as a silent wanderer in the cosmic expanse. The presence of anomalies in composition, trajectory, and energetic behavior sparked vigorous debate within the scientific community. Conferences, online forums, and research groups became arenas where alternative interpretations were rigorously examined. Some astronomers emphasized a natural origin, 3I Atlas, as a relic of planetary formation in another star system, shaped by collisions, differentiation, and ejection processes. Its peculiar nickel abundance, while unusual, could be reconciled with models of core fragmentation or selective loss of more volatile elements, suggesting that nature alone could account for much of the observed behavior. Others, however, adopted a more cautious approach, highlighting the combination of factors that seemed difficult to reconcile solely with conventional astrophysics. The alignment with the wow signal, the trajectory precisely following the planetary plane, and the unusual mass-to-composition ratios prompted some to consider, at least hypothetically, the possibility of non-natural influences. Even without invoking intelligent design, these discussions expanded to include rare astrophysical phenomena, naturally occurring nuclear reactors within metallic-rich objects, magnetic flux interactions producing localized emissions, or unprecedented surface chemistry triggered by long interstellar exposure. Each hypothesis was subjected to scrutiny, constrained by observation, and modeled mathematically to assess plausibility. This debate also underscored the scientific rigor applied to extraordinary claims. Researchers meticulously catalogued data, compared observations against predictions, and eliminated sources of error before entertaining more speculative interpretations. Peer review, cross-validation between observatories, and repeated measurement were emphasized, ensuring that conjecture remained grounded. The scientific discourse illustrated a delicate balance, openness to possibility tempered by adherence to empirical evidence, an approach that honors both curiosity and methodological integrity. Importantly, the discussion extended beyond technical modeling to consider epistemological questions. How do humans interpret anomalies that challenge existing frameworks? 3I Atlas became a mirror, reflecting the limits of current knowledge and the frameworks through which we interpret the cosmos. Debates over natural versus technological origins were not only about the object itself, but about how humans construct understanding in the face of incomplete information, weighing probability, physics, and the unexpected. The debate also had practical implications. Observation strategies, data allocation, and instrument calibration were informed by the diversity of interpretations. Teams adjusted spectroscopic monitoring to detect any unusual emissions, tracked rotational behavior to observe mechanical stability, and monitored the evolving tail to understand material loss. Each measurement could either reinforce or challenge prevailing models, making the object an active participant in shaping the trajectory of inquiry itself. Ultimately, the scientific debate surrounding 3I Atlas highlights the richness of modern astronomy. It exemplifies how anomalies catalyze investigation, foster collaboration, and expand conceptual boundaries. While consensus leaned toward a natural origin, the process of questioning, testing, and revising models embodies the essence of science, a dynamic interplay between observation, theory, and the inexhaustible curiosity that drives humanity to seek understanding amid the vast uncertainties of the universe. Theoretical models for 3I Atlas extend across a spectrum that encompasses both established astrophysical mechanisms and speculative yet physically plausible scenarios. At one end lies the conventional interpretation, 3I Atlas, as a fragment ejected from a distant planetary system, its composition reflecting differentiation processes in a parent body. Nickel-rich cores could have survived collisional stripping, while less dense materials, including iron-rich layers or volatiles, were removed during ejection. Over millions of years of interstellar travel, cosmic radiation, micrometeorite impacts, and thermal cycling could have altered surface layers, producing the observed anomalies in spectral data. This natural framework situates the object within known physical laws, while accommodating its unusual chemical signature and high velocity. A second class of models explores exotic natural processes. Could an internal, naturally occurring energy source, analogous to a small-scale nuclear reactor, exist within a metallic-rich fragment, capable of producing intermittent radiation or affecting particle ejection? Although rare, such mechanisms are not impossible within extreme astrophysical contexts, and they could account for subtle anomalies in observed emissions. These models require precise parameterization, from decay rates to energy transfer mechanisms, and are constrained by the object's observed mass, velocity, and trajectory. Simulations allow researchers to test whether such internal processes could realistically produce detectable effects while remaining consistent with other observed characteristics. Speculative models venture into the domain of hybrid or technological hypotheses. While the probability remains low, consideration is given to the notion that an interstellar probe, ancient and metallic-rich, might exploit natural materials to generate detectable energy or communicate signals. These scenarios are evaluated rigorously, with careful attention to what can be observed versus what must be inferred. The exercise is not to claim technological origin, but to explore boundaries of plausibility, ensuring that natural explanations are exhausted and that observational campaigns can account for all potential mechanisms without prejudice. In this sense, 3I Atlas functions as both a subject of study and a catalyst for methodological reflection, challenging scientists to maintain openness without compromising rigor. Cosmic dynamics further inform these models. The hyperbolic trajectory, alignment with the planetary plane, and extreme velocity-constrained mass, density, and surface properties. Simulated interactions with solar radiation pressure, gravitational perturbations, and material loss provide a framework within which different hypotheses are tested. Models predict rotational behavior, tail formation, and trajectory stability under a range of conditions, allowing empirical observation to serve as a decisive arbiter between competing theories. Observers can then prioritize measurements that maximize discriminatory power, targeting features that are sensitive to specific assumptions about composition and internal structure. Ultimately, these theoretical explorations illustrate the interplay of imagination and empiricism in modern astronomy. 3I Atlas is simultaneously a natural puzzle, a laboratory for extreme physics, and a canvas for considering possibilities at the edge of experience. Each model, grounded in observation and constrained by physical law, expands our understanding of interstellar material and the diversity of processes capable of producing anomalous objects. In contemplating its nature, scientists navigate the delicate balance between the known and the unknown, creating frameworks that honor both rigorous measurement and the vast, unpredictable richness of the cosmos. Instrumentation plays a critical role in deciphering the mysteries of 3I Atlas, serving as the interface between human inquiry and interstellar reality. The capabilities of Mars orbiters, ground-based telescopes, and Earth-orbiting observatories allow scientists to capture multispectral data, measuring reflected light, elemental composition, and even subtle changes in rotational state. Each instrument contributes a distinct perspective. High-resolution cameras resolve surface features and tail morphology. Spectrometers parse chemical abundances, and photometers track variations in brightness that may reveal rotation or topographical irregularities. Together, these instruments form an interlocking network, enabling a comprehensive observational approach that transforms fleeting photons into a rich, multidimensional dataset. The challenge lies not only in the technical capabilities but in the orchestration of data acquisition. 3I Atlas moves rapidly, limiting the temporal window for optimal imaging. Orbital mechanics dictate precise timing for observations, requiring coordination across multiple platforms to ensure that no opportunity is lost. Ground-based telescopes complement orbital assets, providing broader temporal coverage and redundancy in case of instrumental limitations. Observers calculate optimal exposure times, account for Doppler shifts, and implement algorithms to correct for motion blur, atmospheric distortion, and background interference. Every measurement is the product of meticulous planning and real-time adaptation, reflecting the precision required to study an object hurtling through space at 60 kilometers per second. Instrumentation also facilitates the detection of subtle phenomena. The shedding of nickel-rich particles, for example, generates faint spectral signatures that must be separated from background noise. Variations in brightness may indicate rotation, precession, or localized outgassing. Sensitive radio instruments search for transient emissions that might provide clues about internal energetic processes or interactions with solar radiation. The combination of multi-wavelength observations ensures that both expected and unexpected behaviors can be captured, creating a holistic view of the object that integrates physical, chemical, and mechanical information. Moreover, the instrumentation embodies a dialogue between technology and theory. Each observation is guided by predictive models, which in turn are refined as data streams in. Discrepancies between expected and observed behavior inform revisions to mass estimates, density calculations, and models of surface activity. This iterative process exemplifies the scientific method in action. Instruments collect data, models predict outcomes, and each informs the refinement of the other. For 3I Atlas, this feedback loop is essential, as direct sampling is impossible, and every photon carries the weight of inference and interpretation. Finally, instrumentation extends beyond human perception, bridging distances that are otherwise insurmountable. It transforms faint signals into measurable phenomena, allowing the object to be studied with a precision and depth that mere observation could never achieve. In doing so, it enables not only the analysis of physical properties but also the broader philosophical engagement with an interstellar visitor, a silent traveler made intelligible through human ingenuity, patience, and the relentless application of technological insight. Through these tools, the universe communicates its subtle messages, and humanity listens, interprets, and learns. The motion of 3I Atlas is a symphony of celestial mechanics, a choreography dictated by interstellar origins, gravitational influences, and the subtle forces of the solar system. Its hyperbolic orbit carries it through the inner solar system at unprecedented speeds, a trajectory that is not only rare but also revealing. By examining its motion, scientists gain insight into its mass, internal structure, and interaction with the surrounding environment, allowing them to infer properties that cannot be measured directly. Rotational dynamics play a pivotal role in interpreting its behavior. Photometric variations observed over time suggest a rotation that may be irregular, potentially influenced by asymmetric mass distribution or surface heterogeneity. Spin, in turn, affects the distribution of shedding material, shaping the tail and altering the object's angular momentum. Even minor deviations in rotation can propagate into measurable changes in trajectory, providing indirect evidence of density variations, surface fractures, or internal cavities. These subtle mechanical effects, when analyzed in concert with trajectory models, help reconstruct the three-dimensional structure of the object. The hyperbolic trajectory also offers clues to the object's provenance. Unlike bound solar system objects, 3I Atlas is not returning along a periodic orbit. It is a visitor from afar, likely ejected from a distant star system. Its velocity, combined with the orientation of its approach, allows astronomers to backtrack its path through interstellar space. estimating the potential origin regions within the galaxy. Such analyses are probabilistic, constrained by gravitational interactions with other stars, interstellar medium drag, and perturbations from massive bodies encountered during transit. Nevertheless, these reconstructions yield a picture of interstellar dynamics, illustrating the journey of material across light years and time. Interactions with planetary bodies, particularly Mars, provide additional layers of insight. While the object's high velocity renders gravitational perturbations minimal, close approaches allow for precise measurement of trajectory deflections, offering a natural experiment in applied celestial mechanics. By monitoring the object as it passes near Mars, scientists can refine models of its mass, rotational stability, and potential structural anisotropies. Even slight changes in speed or direction serve as valuable data points, encoding information about internal density distribution and material response to tidal forces. Subtle influences from solar radiation and the solar wind further complicate motion analysis. Ejected particles, photons imparting momentum, and magnetically influenced charged particles introduce minute but measurable effects on trajectory. By correlating these effects with observed tail structure and composition, researchers can test theories regarding surface properties, cohesion, and energy transfer mechanisms. Each component of motion linear, rotational, and perturbative interweaves to form a complex yet decipherable narrative of physical properties. Philosophically, the study of 3I Atlas's motion highlights the elegance of natural law. A solitary interstellar object, moving hundreds of times faster than any terrestrial vehicle, obeys the immutable rules of physics while simultaneously challenging the limits of human observation and understanding. Its path is both predictable and extraordinary, a testament to the deterministic beauty of celestial mechanics intertwined with the randomness of interstellar ejection. Observing its motion provides not only practical insight, but also a meditation on the harmony of forces acting across space, offering a glimpse into the subtle, interconnected dance of the cosmos. The collection of data from 3I Atlas is only as meaningful as the ability to process and interpret it, and this task presents challenges as complex as the object itself. Instruments capture streams of photons, spectra, and positional coordinates, each interlaced with background noise, instrumental artifacts, and cosmic interference. Raw images reveal only the faintest traces, requiring correction for motion blur, light scattering, and detector imperfections. Sophisticated algorithms, cross-calibration, and modeling are essential to extract reliable information from these subtle signals, transforming ephemeral glimpses into quantitative data that can inform physical understanding. The processing of spectral data is particularly nuanced. Observers analyze absorption and emission lines to infer elemental composition, yet interstellar travel modifies these signatures. Cosmic rays, radiation exposure, and collisions with microscopic particles alter surface chemistry, sometimes producing spectral features that mimic unfamiliar compounds. Separating these effects from genuine anomalies demands a combination of theoretical modeling and empirical calibration. Analysts must account for instrument response, thermal noise, and transient environmental factors while integrating data across multiple instruments to build a coherent spectral map of the object. Temporal factors add another layer of complexity. 3I Atlas moves at 60 kilometers per second, completing substantial portions of its trajectory within hours. Observational windows are fleeting, and missing a sequence of images or spectral measurements could eliminate critical information about rotation, outgassing, or tail morphology. Processing pipelines therefore prioritize real-time or near real-time analysis, flagging anomalies, adjusting exposure parameters, and coordinating follow-up observations across ground-based and orbital platforms. The integration of automated analysis with human interpretation ensures both precision and adaptability, a fusion of algorithmic efficiency and expert intuition. Material loss and surface activity are interpreted through the combination of photometric and spectral data. Changes in brightness may indicate rotational modulation or localized shedding, while the composition of ejected particles informs models of internal structure. Detecting such subtleties requires not only high-resolution imaging, but also time series analysis, correlating changes with orbital mechanics, solar radiation pressure, and thermal cycles. Processing these data allows scientists to infer internal density variations, mechanical stability, and surface heterogeneity, bridging observation and modeling in a continuous feedback loop. Beyond technical challenges, data processing embodies philosophical reflection. The universe communicates through light and energy, subtle and dispersed, yet human ingenuity transforms these faint signals into understanding. Each corrected pixel, calibrated spectrum, and reconstructed trajectory represents a step closer to decoding the object's story, allowing 3I Atlas to reveal the history of distant stellar environments, interstellar travel, and material evolution. Processing is not merely computation, it is interpretation, an act of listening to the cosmos and translating its whispers into a narrative comprehensible to human intellect. In this sense, the challenges of data interpretation are inseparable from the pursuit of meaning. 3I Atlas becomes both object and teacher, presenting obstacles in processing that reflect the broader difficulty of bridging vast distances and subtle signals. The careful extraction of information, the discernment of pattern from noise, and the synthesis of disparate measurements illustrate the art of modern astronomy, where data and insight converge to illuminate the nature of an interstellar traveler crossing the solar system with silent majesty. The composition of 3I Atlas deepens the mystery as observations reveal more nuanced anomalies in elemental abundance. Beyond the pronounced nickel-rich signature, subtle deviations in other trace elements and isotopic ratios suggest processes unrecorded in our local solar system. For example, minor emissions detected in spectral lines hint at the presence of unusual oxides or sulfides, compounds that are not typically found in comets or asteroids originating near the Sun. These patterns indicate that the object has undergone conditions, whether thermal, radiative, or collisional, that differ significantly from familiar planetary material, pointing to the diversity of environments in interstellar space. Material heterogeneity is another critical aspect. Observations suggest that certain regions of 3I Atlas may be enriched with metallic compounds, while other areas remain relatively inert, implying that the body is not uniform but rather a complex aggregation of matter with varied history. This patchwork may reflect a layered structure inherited from a larger progenitor, exposure to differential solar radiation, or impact events during its ejection and journey. Mapping these differences is essential for understanding both the mechanical integrity of the object and the processes that shaped it across light years. Furthermore, the shedding of material interacts with composition in intricate ways. As nickel-rich particles are ejected, they alter the local mass distribution, influencing rotational dynamics and subtly shifting trajectory vectors. Spectroscopic analysis of the tail allows astronomers to identify which elements are preferentially lost, providing indirect clues to density, bonding strength, and thermal properties of the surface layers. This interplay between composition and motion creates a self-reinforcing feedback loop, where observations of one property inform models of another, gradually revealing a multidimensional picture of the interstellar traveler. Chemical anomalies also spark broader inquiry into stellar and planetary formation beyond our solar system. If such nickel-rich fragments exist in other star systems, they may reflect formation in high metallicity environments, the aftermath of supernovae, or differentiated planetary cores disrupted and ejected by gravitational interactions. Each inference carries implications not just for 3I Atlas, but for our understanding of the diversity of matter in the galaxy, the prevalence of metallic bodies, and the potential for extreme variations in interstellar debris. Finally, these compositional mysteries reinforce the philosophical dimension of observation. 3I Atlas, a solitary object traversing light years, carries within it the record of processes beyond human reach, encoded in the subtle balance of elements, isotopes, and structural patterns. For astronomers, deciphering these clues is an exercise in humility and imagination, bridging empirical rigor with contemplative inquiry. The object's chemical story is a narrative of the cosmos itself, a testament to the diversity, complexity, and interconnectedness of processes operating on scales both vast and minute. The cosmic implications of 3I Atlas extend far beyond the object itself, offering profound insight into the nature of planetary systems and the material that traverses interstellar space. Every fragment, every trace of ejected nickel, carries a record of formation processes occurring far from the Sun, illuminating conditions in distant star systems that might otherwise remain forever beyond observation. By studying this interstellar visitor, scientists gain not only an understanding of a single object, but a glimpse into the diversity and dynamics of the galaxy at large. 3I Atlas challenges assumptions about the frequency and composition of interstellar debris. Prior discoveries, such as Oumuamua and 2I Borisov, hinted at the variety of objects that might traverse the void, yet this body introduces new parameters: a high nickel content, a trajectory closely aligned with the ecliptic plane, and a mass substantial enough to influence its motion and observational profile. These characteristics suggest that the processes forming interstellar objects are more diverse and perhaps more extreme than previously understood, implying that other planetary systems may produce bodies with unusual compositions and unexpected structural integrity. The passage of 3I Atlas also informs models of planetary system evolution. Its ejection from a distant system and subsequent traversal across light years exemplify the dynamism of stellar environments, where collisions, gravitational perturbations, and radiation can expel fragments into interstellar space. By analyzing its composition and motion, astronomers can infer properties of its parent system, metallic abundance, history of planetary differentiation, and collisional events. These inferences, while indirect, expand knowledge of how material circulates across the galaxy, contributing to broader theories of planetary formation and evolution beyond the solar system. Interstellar objects like 3I Atlas also illuminate the potential for seeding or exchanging material across star systems. While this remains speculative, the idea that fragments of planetary cores, metallic-rich debris, or organic-rich bodies may traverse vast distances introduces possibilities for material exchange that could influence planetary chemistry, prebiotic processes, or even the distribution of rare elements. Observations of composition, trajectory, and structural integrity thus have ramifications not only for astrophysics, but also for broader cosmochemical and astrobiological considerations. Philosophically, the implications extend to humanity's understanding of cosmic context. The realization that material from distant systems can reach our solar system challenges notions of isolation, emphasizing the interconnectedness of stellar neighborhoods. Each interstellar object is a messenger, a physical record of processes far from Earth, inviting reflection on the scale of time, distance, and causality in the galaxy. Observing 3I Atlas fosters awareness that our planetary system is part of a dynamic galactic ecosystem where matter and energy flow across space in ways that intertwine with countless unknown histories. Ultimately, the cosmic significance of 3I Atlas lies not only in its anomalous properties, but in its ability to illuminate fundamental questions about the universe. It serves as a tangible connection to distant stars, a data-rich artifact that bridges observational astronomy, theoretical modeling, and philosophical reflection. By studying its passage, scientists gain insight into the mechanics, chemistry, and evolution of interstellar matter, enriching understanding of both the galaxy's architecture and the subtle, intricate processes that govern the formation and migration of celestial bodies across vast expanses. The hypothesis that 3I Atlas might harbor technological aspects remains speculative, yet it is a topic that commands rigorous scientific consideration. While the object's behavior and composition are broadly consistent with natural processes, the possibility, however, remote of non-natural influences cannot be dismissed outright. The alignment with the wow signal, unusual nickel-to-iron ratios, and precise trajectory along the planetary plane invite thought experiments grounded in physics, prompting researchers to consider what natural processes might produce similar signatures and whether any plausible mechanism could mimic technological activity. One avenue explored is the potential presence of energy-generating mechanisms within the object. A metallic-rich core, compact and dense, could theoretically support localized thermal or radioactive activity sufficient to produce detectable emissions. This could manifest as low-level radio waves, thermal anomalies, or particle ejection patterns that depart subtly from expected behavior. While purely natural in origin, these processes might be mistaken for signs of purposeful energy management, if not rigorously contextualized, illustrating the importance of modeling all plausible physical mechanisms before entertaining technological interpretations. In parallel, models of directed or structured emission, even hypothetical, are examined for boundary conditions. If 3I Atlas were artificially equipped with an energy source, constraints imposed by mass, composition, and observed motion define the scale, duration, and intensity of any signals it might produce. Researchers simulate these parameters to assess whether observed phenomena, such as faint radio emissions or transient tail anomalies, could feasibly originate from such mechanisms. The goal is not to assert intelligent origin, but to establish observational criteria capable of distinguishing between natural and highly improbable artificial processes. The examination of technological hypotheses also serves as a methodological exercise, sharpening the precision of scientific inquiry. By testing extreme scenarios, scientists identify weaknesses in observational protocols, improve instrument calibration, and define limits for interpretation. Each what-if scenario informs the collection and analysis of data, ensuring that every measurement is considered in light of both conventional and extraordinary possibilities. In doing so, 3I Atlas acts as a crucible for methodological rigor, compelling researchers to anticipate, model, and test a broad spectrum of outcomes. Philosophically, contemplating technological hypotheses highlights the interplay between imagination and evidence. The human mind is naturally inclined to attribute agency, to seek patterns and intent, yet astronomy demands a disciplined approach. Considering the full spectrum of possibilities while rigorously constrained by physics exemplifies scientific humility, acknowledging that the universe may produce phenomena at the edge of expectation and that inquiry must remain open without succumbing to conjecture. In this delicate balance, 3I Atlas becomes more than a celestial object. It becomes a teacher, illustrating the boundaries of certainty, the necessity of skepticism, and the creative rigor that underpins scientific exploration. Ultimately, the exercise of exploring technological possibilities reinforces the importance of comprehensive observation and critical analysis. By integrating spectral, photometric, and motion data with theoretical modeling, scientists ensure that all plausible explanations are considered, constrained, and tested. In doing so, the enigmatic nature of 3I Atlas serves as both a catalyst for inquiry and a mirror reflecting the expansive, disciplined curiosity required to study interstellar phenomena, where the improbable must be weighed and the unknown must be approached with both rigor and imagination. The passage of 3I Atlas invites not only technical analysis but also philosophical reflection, emphasizing the emotional and cognitive resonance of encountering an interstellar visitor. Beyond measurements, calculations, and models, the object confronts humanity with the scale and mystery of the cosmos, prompting introspection about our place in the galaxy. The sight of a 3-mile fragment traveling at 60 kilometers per second, shaped by forces beyond Earth's influence, stimulates wonder, humility, and the recognition of both our limitations and capabilities as observers. Philosophical reflection begins with temporality. 3I Atlas carries within it a record of events spanning millions, perhaps billions of years. Collisions in distant star systems, ejection from a planetary system, and a solitary journey across interstellar space. Each particle, each chemical signature, is a fragment of cosmic history, arriving at a precise moment to intersect human observation. Witnessing its passage reminds humanity that time in the cosmos operates on scales that dwarf our daily experience, and that brief windows of observation can offer profound insights into processes otherwise inaccessible. The encounter also provokes contemplation of agency and purpose. While the object moves without intent, aligning coincidentally with historical signals and planetary planes, humans naturally project curiosity, narrative, and interpretation onto its motion. This interplay between the object's indifference and human perception elicits questions about meaning in the universe. Are coincidences merely statistical inevitabilities, or do they reflect underlying principles we have yet to discern? Philosophical engagement with 3I Atlas requires balancing rational inference with awe, acknowledging both the object's autonomy and our interpretive lens. Furthermore, 3I Atlas highlights the interconnectedness of celestial systems. Its journey from a distant star across light years to the inner solar system demonstrates the mobility of matter on a galactic scale. Chemical elements, gravitational forces, and cosmic radiation interweave across immense distances, producing objects that convey the histories of environments far removed from our own. Observing and interpreting these connections fosters a holistic perspective on the galaxy, one that blends astrophysics with a sense of cosmic narrative, situating Earth and Mars within a broader, dynamic tapestry. Philosophical reflection extends to the practice of science itself. Observing 3I Atlas exemplifies human curiosity, patience, and ingenuity. The meticulous orchestration of instruments, the careful processing of data, and the iterative refinement of models reveal the depth of our commitment to understanding phenomena that cannot be directly touched or altered. The object's silent voyage becomes a mirror, reflecting humanity's desire to comprehend, to find order, and to derive insight from the vast, indifferent universe. In this way, the act of observation is both technical and existential, a blending of rigor and wonder. Finally, contemplating 3-Eye Atlas encourages a meditation on uncertainty and humility. Despite sophisticated models and advanced instruments, the object retains elements of unpredictability. Its precise composition, internal structure, and potential energetic behaviors remain partially obscured. This uncertainty, rather than discouraging inquiry, enriches the encounter, inviting reflection on the provisional nature of knowledge and the necessity of embracing the unknown. In its passage, 3-Eye Atlas embodies both the limits of human understanding and the infinite possibilities of discovery, serving as a cosmic touchstone for curiosity, reflection, and philosophical engagement. Even as 3-Eye Atlas continues its swift passage past Mars, plans for future tracking extend well beyond the immediate flyby, reflecting the long-term value of interstellar observation. Orbital assets and ground-based facilities remain poised to follow the object as it recedes from the inner solar system, capturing successive measurements that can refine trajectory, rotational dynamics, and compositional understanding. This extended observation strategy ensures that data from the brief encounter is maximized, allowing scientists to trace subtle changes and continue testing models developed during the close approach. Predictive modeling is central to these efforts. By simulating its future motion, astronomers calculate when and where the object will be optimally visible to various instruments, accounting for factors such as distance, illumination, and the effects of solar radiation pressure. These forecasts guide scheduling of telescope time, orbital instrument orientation, and coordination among observatories. Even small errors in trajectory predictions can compound over the vast distances involved, making early, high-precision measurements critical for accurate long-term tracking. Extended observation also enhances the ability to monitor structural and compositional evolution. As 3-Eye Atlas moves farther from Mars and the Sun, the thermal environment changes, potentially affecting outgassing, surface stress, or rotational dynamics. Continuous monitoring allows scientists to detect shifts in brightness, tail morphology, or spectral signatures that may indicate further material loss or alterations in surface composition. Each observation feeds back into models, improving predictions and informing future interpretations of both 3-Eye Atlas and similar interstellar objects. In addition to physical tracking, future monitoring includes attempts to capture faint electromagnetic signals, both to test natural emission hypotheses and, however unlikely, to constrain possibilities of technological features. Instruments sensitive to radio frequencies, magnetic field perturbations, and thermal anomalies remain engaged, prepared to detect any transient or weak signals. While no definitive evidence has yet emerged, these observations establish critical upper limits and refine expectations for future interstellar visitors, shaping methodologies for detection and analysis. Philosophically, continued tracking underscores the persistence and patience required in astronomical inquiry. Unlike terrestrial phenomena, which can be studied repeatedly and manipulated, interstellar objects offer fleeting opportunities for observation. Long-term monitoring embodies a commitment to understanding phenomena that exist on scales and velocities far removed from daily human experience. Each measurement, whether confirming prior models or revealing subtle deviations, strengthens the connection between human curiosity and the vast, indifferent universe, reinforcing the principle that discovery is often incremental, cumulative, and shaped by both precision and perseverance. Ultimately, future tracking transforms 3-Eye Atlas from a transient flyby into a longitudinal study. By following its journey, scientists not only capture the evolving behavior of a single interstellar object, but also refine the tools, techniques, and frameworks necessary to study other, yet-to-be-discovered visitors. In this way, the ongoing observation becomes a bridge across time and space, linking the present encounter to a broader effort to understand the interstellar environment, the diversity of cosmic matter, and the intricate dance of forces that govern objects traveling across the galaxy. Comparative studies place 3I Atlas in context alongside previous interstellar visitors, particularly Oumuamua and 2I Borisov, highlighting both commonalities and distinctions that illuminate broader astrophysical principles. Oumuamua, detected in 2017, presented as an elongated, highly reflective object with little to no observable outgassing, sparking debate about its natural versus potentially artificial nature. In contrast, 2 Borisov, discovered in 2019, exhibited conventional cometary characteristics, ice-rich, producing a visible coma and tail, with spectral signatures consistent with solar system comets. 3I Atlas, by combining anomalous composition, substantial mass, and an unusually aligned trajectory, offers a bridge between these examples, expanding the taxonomy of interstellar objects and revealing new parameters for observation and interpretation. Studying 3I Atlas in comparison with its predecessors enhances understanding of formation and ejection mechanisms. The diversity of physical and chemical characteristics across these interstellar bodies suggests that the processes capable of ejecting material from planetary systems are more varied than previously assumed. While Oumuamua may represent a thin, elongated fragment or surface-altered body, and Borisov a conventional icy comet, 3I Atlas exemplifies a massive, metallic-rich fragment, hinting at the ejection of differentiated material from planetary cores or collisional debris fields. These distinctions inform models of stellar system evolution, planetary differentiation, and the prevalence of interstellar fragments with unusual properties. Comparative analysis also informs observational strategy and interpretation. Differences in speed, size, trajectory, and composition among the 3 objects allow astronomers to refine expectations for future detections. Observing how each object interacts with solar radiation, gravitational fields, and interplanetary matter provides empirical benchmarks for predicting the behavior of subsequent interstellar visitors. By contrasting 3I Atlas with Oumuamua and Borisov, researchers calibrate models of material loss, rotational dynamics, and spectral variation, enabling more accurate assessments of physical properties and internal structure. Furthermore, comparative studies enrich philosophical reflection on interstellar material. Each object represents a tangible connection to distant planetary systems, yet the variation among them underscores the heterogeneity of cosmic processes. The presence of metallic, icy, and structurally unique interstellar objects suggests that galactic environments produce a spectrum of matter, each with its own history and trajectory, weaving a complex tapestry of stellar evolution, collisions, and ejection. Observing 3I Atlas, alongside its predecessors, invites consideration of the galaxy, not as a static backdrop, but as a dynamic laboratory of creation, destruction, and dispersal. Finally, the act of comparison fosters methodological rigor. By situating 3I Atlas within a lineage of interstellar bodies, scientists can test hypotheses against known examples, evaluate the consistency of models, and refine criteria for anomaly detection. This comparative lens transforms individual observation into cumulative understanding, highlighting both the novelty of 3I Atlas and its contribution to an evolving framework for studying interstellar matter. In this way, each object, past and present, informs not only our comprehension of specific events, but also the broader principles governing material exchange across the galaxy. The fascination with 3I Atlas extends beyond the scientific community, reaching the public imagination and highlighting the intersection of media, communication, and space exploration. News outlets, social media platforms, and public lectures transformed a fleeting interstellar event into a shared cultural moment, inviting curiosity, speculation, and emotional engagement. Headlines emphasized its interstellar origin, anomalous composition, and proximity to Mars, framing the object as both a scientific marvel and a narrative spectacle. The public response underscores humanity's enduring desire to connect with phenomena that transcend everyday experience, where science, wonder, and storytelling intersect. Media coverage also shaped perception of uncertainty and risk. Although the object posed no direct threat, its unusual features and velocity, combined with references to historical anomalies like the wow signal, created a narrative tension that captivated audiences. Scientists engaged with the public to clarify the parameters of observation, explain the natural mechanisms at work, and temper sensational speculation, balancing transparency with rigor. In doing so, the encounter with 3I Atlas became an opportunity for science communication, illustrating how complex astronomical phenomena can be conveyed meaningfully while retaining nuance and context. The interplay between media and scientific observation had practical consequences. Public interest heightened scrutiny of observational campaigns, increased support for funding telescope time, and accelerated data-sharing protocols. Observatories adapted to heightened attention, producing visuals, explanatory materials, and real-time updates to engage a global audience. This reciprocal dynamic illustrates the evolving role of public engagement in astronomy. The visibility of a celestial event can influence research priorities, resource allocation, and collaborative efforts, transforming observation from an isolated scientific endeavor into a participatory experience. Furthermore, public fascination intersects with philosophical reflection. Witnessing a 3-mile interstellar traveler pass near Mars prompts contemplation of scale, distance, and temporal perspective. It encourages reflection on humanity's place within a vast galaxy, the serendipity of observation, and the humility required to appreciate phenomena that operate on timescales and distances far beyond daily experience. The cultural impact of 3I Atlas illustrates how scientific observation transcends data collection, fostering collective reflection on the universe's complexity and mystery. Finally, the convergence of science and media emphasizes responsibility in interpretation. By providing accurate context, avoiding undue speculation, and highlighting the provisional nature of understanding, scientists and communicators reinforce public trust while nurturing curiosity. 3I Atlas thus serves not only as a subject of study, but also as a catalyst for civic engagement with astronomy, inspiring wonder, promoting literacy in science, and reminding humanity that the cosmos offers lessons not solely in physics, but in observation, reflection, and shared experience. Despite the wealth of data gathered, 3I Atlas leaves a profound sense of unresolved mystery. Numerous questions remain unanswered, from the precise mechanism behind its nickel-rich composition to the reasons for its unusually aligned trajectory. Observers can measure position, velocity, rotation, and tail morphology, yet the deeper processes that shaped its formation billions of years ago and dictated its journey across interstellar space remain partially veiled. Each new observation answers some questions while simultaneously opening others, preserving a tension that fuels both scientific investigation and philosophical contemplation. The transient nature of the encounter contributes to the enigma. As the object recedes from Mars and the Sun, observational opportunities diminish, imposing strict temporal constraints on measurement. Even with advanced orbiters and telescopes, capturing high-resolution imagery and precise spectroscopic data is limited to brief windows. This scarcity reinforces the sense that 3I Atlas is both ephemeral and consequential, a visitor whose passage allows only partial comprehension, highlighting the limitations inherent in studying objects that traverse vast distances at extreme velocities. Uncertainty extends to internal structure and potential energetic processes, while modeling provides estimates of density, cohesion, and rotational dynamics. Direct observation of the interior is impossible. Hypotheses regarding natural or exotic mechanisms for energy release, tail formation, or signal generation remain constrained by indirect measurements. Scientists must balance speculation with rigor, ensuring that each inference is grounded in observable phenomena while acknowledging the provisional nature of conclusions. Additionally, broader implications remain unresolved. The apparent alignment with the WOW signal, while intriguing, cannot definitively establish causation. Statistical probability, observational limitations, and alternative natural explanations all contribute to an enduring ambiguity. Similarly, questions about the object's origin, whether from a planetary system with high metallicity, a fragment of a differentiated body, or an entirely unexpected environment, remain open. Each scenario carries implications for models of interstellar object formation, planetary system dynamics, and galactic material exchange, underscoring the broader significance of unanswered questions. Philosophically, this uncertainty emphasizes the humility required in astronomical inquiry. 3I Atlas embodies the universe's capacity to challenge expectation, blending the known and the unknown in a single observable event. Its mysteries invite reflection on the provisional nature of knowledge, the patience required in scientific pursuit, and the persistent drive to interpret fleeting phenomena. By grappling with these unresolved questions, humanity not only advances understanding of a unique interstellar object, but also confronts fundamental aspects of observation, inference, and the limits of comprehension in a cosmos of vast scale and complexity. From a cosmic perspective, 3I Atlas emphasizes the interconnectedness of celestial systems and the vast scale of the galaxy. Its passage through the inner solar system is not an isolated event. It reflects the broader dynamics of matter traveling between star systems, illustrating how interstellar material circulates and occasionally intersects with planetary neighborhoods. Observing its motion and composition offers insight into the physical and chemical processes operating on galactic scales, extending understanding beyond the local context of the Sun and its planets. The object's journey underscores the dynamism of the Milky Way. Stars form, evolve, and shed material. Planetary systems interact gravitationally, and debris, once ejected, traverses light years to encounter other systems. 3I Atlas is a tangible manifestation of these processes, a fragment of a distant environment shaped by forces far beyond Earth's influence, yet momentarily accessible to human observation. Its trajectory, velocity, and composition encode information about interstellar travel, the prevalence of metallic-rich debris, and the potential variety of planetary formation histories across the galaxy. Observing 3I Atlas also situates humanity within this cosmic network. By tracking, modeling, and analyzing the object, scientists engage with material that has journeyed across vast expanses of space, integrating knowledge of distant systems with local observation. This perspective reinforces the notion that the solar system is not isolated, but part of an interconnected galactic ecosystem where matter and energy continuously circulate, collide, and evolve. Each interstellar object is both a messenger and a probe, providing empirical evidence of processes that would otherwise remain theoretical. The passage invites reflection on temporal scale. 3I Atlas likely left its parent system millions of years ago, drifting silently through the interstellar medium before intersecting the solar system. Observing it now connects human timescales with cosmic timescales, bridging epochs in which distant planetary systems formed, evolved, and ejected fragments. This temporal perspective emphasizes the fleeting nature of the encounter, highlighting the rare opportunity for observation and the value of meticulous planning, coordination, and interpretation in capturing insights from such ephemeral events. Finally, the cosmic perspective encompasses philosophical resonance. 3I Atlas illustrates the universe's vastness, the mobility of matter, and the interplay of forces across incomprehensible distances. Its passage transforms abstract understanding into tangible observation, linking human inquiry to processes that operate far beyond immediate perception. By contemplating the galaxy-wide context of the object, observers gain both technical insight and a deeper sense of place within the cosmos, appreciating the elegance, complexity, and scale of the interstellar dynamics that bring such rare travelers into view. As 3I Atlas reaches the far side of its flyby past Mars, reflection deepens on the significance of the encounter, both scientifically and philosophically. The object's passage has yielded an unprecedented wealth of data, high-resolution images capturing surface heterogeneity, spectra revealing anomalous chemical signatures, rotational analysis informing internal structure models, and trajectory measurements testing predictions of interstellar dynamics. Yet, despite these accomplishments, the interstellar traveler retains elements of enigma, reminding humanity of the universe's complexity and the limits of observation. The synthesis of data across multiple instruments and platforms underscores the collaborative nature of modern astronomy. Mars orbiters, ground-based telescopes, and Earth-orbiting sensors collectively transform fleeting photons into coherent models of mass, composition, and motion. This integrated approach highlights the necessity of interdisciplinary collaboration. Astronomers, physicists, data scientists, and engineers work in concert to reconcile observations with theoretical frameworks, ensuring that interpretations are robust, reproducible, and anchored in physics. 3. ATLAS serves as both a test case and a benchmark, refining methods for studying future interstellar visitors. Philosophically, the encounter evokes contemplation of scale, chance, and temporality. A 3-mile fragment ejected from a distant planetary system and traveling light years to intersect the solar system reminds observers of both the vastness of space and the serendipity of observation. Its fleeting proximity to Mars, a transient alignment with planetary bodies, orbiters, and telescopes, underscores the rare window through which understanding can be gleaned. In this brief moment, humanity touches, however indirectly, phenomena that have unfolded over cosmic timescales, bridging epochs and distances that are otherwise unimaginable. The mysteries that remain are as instructive as the discoveries. Questions about the precise formation conditions, internal energy dynamics, and the potential correlation with historic anomalous signals persist, highlighting the provisional nature of knowledge and the enduring need for observation and modeling. These uncertainties embody the tension between discovery and mystery, illustrating the dual character of science as both a pursuit of explanation and an engagement with the unknown. Ultimately, the passage of 3I Atlas invites reflection on wonder, curiosity, and humility. Its trajectory, composition, and fleeting presence serve as a reminder of the universe's richness, the interconnectivity of stellar systems, and the extraordinary capacity of human observation to engage with phenomena far beyond immediate experience. While many questions remain unanswered, the encounter affirms the power of rigorous inquiry, technological ingenuity, and imaginative reflection in expanding the boundaries of understanding. In the quiet aftermath of the flyby, the object recedes into interstellar space, leaving behind not only data, but an enduring sense of awe and the subtle, unspoken knowledge that the universe holds many more mysteries waiting to traverse our path. The fleeting passage of 3I Atlas across the solar system draws to a close, and with it comes a gentle pause, a moment to reflect on what has been observed, measured, and imagined. The interstellar traveler, 3 miles across and moving at inconceivable speed, retreats into the darkness from which it emerged, leaving behind subtle traces of material, light, and information. These remnants, captured by orbiters, rovers, and telescopes, form a mosaic of understanding, yet they also remind us of the vast unknown that stretches beyond observation, waiting silently in the cosmic expanse. In the quiet aftermath, the mind can wander along the trajectory of the object itself, tracing its journey from distant stars across light years of void to the fleeting encounter with Mars. Each measurement, the nickel-rich particles shed, the faint tail illuminated by sunlight, the rotational patterns and trajectory deviations, becomes a narrative thread connecting distant phenomena with human curiosity and the persistent effort to comprehend what is not immediately graspable. It is a story of motion and matter, of energy and subtle interaction, but also of wonder, humility, and the slow accumulation of insight across time and space. The encounter encourages a meditation on perspective, from the scale of planetary distances to the sweep of interstellar travel, from fleeting seconds of observation to millions of years of cosmic history. 3I Atlas bridges gaps that challenge human perception. Its passage evokes both awe and reflection, a reminder that while our instruments are finite, imagination and careful inquiry allow us to engage meaningfully with the universe's grandeur and complexity. As the object disappears into the interstellar void, it leaves a quiet gift, the knowledge that even a solitary fragment of matter traveling silently across the galaxy can expand understanding, inspire contemplation, and connect humanity to processes unfolding far beyond the bounds of immediate experience. Its journey, now behind us, continues in the fabric of space, a whisper of mystery, a testament to curiosity, and a reminder that the cosmos always has more to reveal. Sweet dreams.